Oh, that's uh, welcome back to Physics 112. I heard that there will be solar eclipse. So if you want to leave early, you can. But it's at 11:07, so there is no reason to leave early. So, but that's, if you want to leave like 5 minutes before, it's not an issue. It should be an issue because you already pay tuition. But if you want to leave early, you can. So we have an iClicker question. So it seems like 50-50. So let's stay the course. I will ask Ross to substitute for me on Wednesday. Okay. So thank you. Next is we have I would call it guest lectures, but they're actually one of them is colloquium speaker. Colloquium is just a different kind of seminar. Colloquium is a day every week when everybody in physics department from cosmology, biophysics, and nanoscience, like we meet, we interact, and we learn to new science. And typically the talk is fairly broad, fairly general. It has a long introduction. So if you are interested, I'm inviting my colleague or my competitor, Professor TJ Ha. He has been a HHMI investigator, which is like one of the highest levels of professorship. He's also the president of Biophysical Society. It's the biggest society in biophysics. He will be giving a talk on Thursday at 3:30. So this is my way to give iClicker to you. So A is yes, B is no. So the question is, are you considering attending TJ's TechJip Has talk? So let's spend like 15 seconds on this. And you don't have to say yes. Okay, good. Okay. Good. So 20 of you, 20 of you are considering attending. So I hope I will see at least one of you. So 1 out of 20 is a good conversion rate. Good enough. Next is, this is my neighbor. My son knows him, Kamran. I saw him this morning, yesterday, chat with him yesterday. He's a eye surgeon at Phoenix Children's Hospital. So he said that, hey, if your student is interested, he volunteers. I didn't ask him. I would be happy to give a guest lecture. So basically, yeah, I can talk about what happened if the refractive index of human eyes is not that good, it's not proper, then what type of disease that thing can cause. So again, this is my way to give you eye clicker point. The question is, if we organize a session, would you attend? A, yes, and B, no. Okay. And let's not spend more than 30 seconds. And it's not binding. Good. So let's close this. So today we will talk about, so today's lecture 27. In terms of the outline of the lecture, we will finish our discussion on flat mirrors, flat mirror. And then we will switch to spherical mirror. Okay, we have this convex and concave mirror. So all of this, so let's take a step back in terms of laws of ray optics. There are two laws. One is, do you guys still remember? One is reflection. The other one is law of refraction. Good. So for mirrors, which law that we use? Just reflection, just refraction, or both? For studying mirrors. For studying mirrors. Which one? Just reflection, both, or just refraction? Mirrors. Reflection, good. Yeah, what's your name? No. Reflection, good. So basically, the angle of incidence is equal to the angle of reflection. And then just to complete our discussion, refraction is when light travels to different medium. The angle of incidence and the angle of refractions follows Snell's law. But we will not use Snell's law today. And you know, this is towards the end of the semester, so I promise that this class will be very useful. This one is, for example, if you are in submerged on the ocean level, and then you want to you have a flashlight and you want to hit the rescue team, you would aim it not straight to the rescue team. You know that light bends, so you aim it at a different angle. First, you calculate Snell's law in your brain, and then you use that angle. You will thank me when you need this. Okay. So flat mirror, we will do applications today. And this one is multiple reflection. And the other one is reflectors. These are really fun. It's a simple physics, but the application is really fun. Spherical mirrors, we only have time to talk about concave mirrors, which mirror that looks like this. So you have an object, you have a focal plane, focal point, and we will study the image formation of concave mirrors. Any question? Okay, so let's start. The first one is a multiple reflection. There is a nice simulator that I found online here. Okay. Close this. So this is basically this one simulate mirrors at an angle, and you can change the angle, I think. And the one that I show in the slide is 90 degrees, and you see 90 degrees mirror in bathroom and many other places. And it's kind of nice because you can see different part of your hair, let's say. So, but just one thing, this simulation is not perfect. You have to play with the angle a little bit. So this is 90 degree, but actually with 90 degree, you can see 4 objects. So you have to move it a little bit. So basically with multiple reflections, you can, so this is experiment that I don't know who was standing here, but basically there is 2 mirrors at 90 degrees angle, okay? And then you know that lights follows law of reflection. So light bounce from the object, which is this person right here, bounce and then hit the mirror and then bounce. But there is our brain extrapolate the lights. Similarly with the other end, our brains also extrapolate the lights, and also light travels to so many directions. Basically, from the front mirror, we get image 1. From the second mirror, not surprisingly, we get image 2. So there is image here and image here. The person is in front of the mirror. Okay, so this is similar to, if you can see my cursor, this image and that image. But actually, if you do a different, like if you study different angles, some of them will bounce multiple times. So for example, this guy, this light will bounce mirror 1, mirror 2, and then bounce. And then you can extrapolate this ray here. And if you do that for many, many rays, or at least 2, you end up with the other image, which is, which my iPhone, wait, this person's iPhone capture as image 3. Okay. So Jennifer, did you learn this when in your high school? No, okay. So when I was in high school, there is a different way to do that, and there is what we call virtual mirror. So mirror actually can be extrapolated, and if you do that, the images can be object for the virtual mirror. Because of that, you get image 3. But this method is less rigorous. I prefer the method that I'm showing you on the screen here. Okay. Any question? So what is the usefulness of multiple reflection? One is in bathroom. You can see different part of your hair. Let's say if you want to fix your hair, multiple refraction can help. So next is, have you seen this object on the road or a bicycle? There is actually one on the surface of the moon. So the name, when I was very young, I was really impressed. I thought that they put battery in it. So what is this? What is this interesting thing? It's, the name of that object is a reflector. This one, I found it from a textbook, but actually it's a 3D object. It's a mirror, and then there's another mirror here. So I don't know how how to draw it, but basically 90 degrees, all 90 degrees, right? So why do we need reflectors? What can be, why reflector is so useful or so interesting? Yeah, Max. All right. Good, good, good. It's save a lot of people's lives. So if you're smart, you can save a lot of people's life. So, and you don't need battery. It just relies on passive. If you don't use energy, we call it passive device. Basically, if you apply the same law of reflection, let's say light comes at an angle I1, and then it will bounce. So I1 is equal to R1. And then if you know that the sum of the angles in a triangle is 180 degrees, then you can figure out what I2, and then using law of reflection, you can calculate R2, and then you can calculate alpha, which is the angle, which is the same as the angle what across the one that I'm highlighting right now. Then with a simple arithmetic, you can find that alpha is equal to I1. What does it really mean? It means like what Max said. If there is a light comes at an angle I or I1, it will get reflected at basically in ideal situation, exactly the same angle as the angle of reflection. Of course, mirror is not completely flat and maybe objects move. So this is really cool. And one thing that I learned when I was taking this class as an undergrad is that it turns out that NASA, when they landed on the moon, so on the Apollo 11 mission, they left an array of reflectors. So this is how NASA refined the measurement of the distance between the moon and the Earth. So basically by shooting laser to reflector and calculate the time between the poles, we can get the distance. The distance is, what is distance? Distance is basically the speed of light times. So if NASA calculated delta t, then they can figure out the distance between the Earth and the moon. Okay. So that's it's a simple device, and of course, many of you use mirrors. Brad Pitt, sorry, every day. Any question before we move to different system? No? Okay. So I will ask you questions about applications on exam 4 and final exams. Okay. This is different than history of science. This is actually part of the class. All right. So far we study reflection that, how to call this? So I hope you still remember the most important concept in optics for this class, which is Fermat's principle of least time. So let me set it up first. So next is, I'm going to show you a spatial case. So next we will talk about spherical mirror or concave mirror. But before that, I want to make it more general. So spherical mirror, like concave mirror, we use it mostly to focus lights. So focusing is a special case. Okay. So there are different geometries that gives multiple paths that lead to least travel time. So I hope you still remember, if you run from parking lot to beach or to sandy beach, then you want to take this path, right? Because this is the path that has multiple, no, that takes the least amount of time. So next is we will study more complex system, which is a path or a system, a geometry that has many paths that takes very short period of time. Okay. But before that, I need to give you a definition of ellipse. Anyone knows definition of ellipse? So ellipse is basically, it looks like this, and it has two focal points. Let's call it F1 and F2. And then the distance between any points on the surface or on the periphery of an ellipse, let's call it R1 and R2, is always the same. So this is a simulation. Basically, if you have a two thumbtacks and you have put a rope of length R1 plus R2, you can make an ellipse. Whoa. Something like that. Okay. So I have a question for you. So let's say we have an ellipse. And in this case, instead of using lenses or mirrors, let's think of it in the context of steel cage. Okay? And you and your enemy, I don't know, from U of A maybe, has one gun with one bullet. Okay? And then the rule is you have to, you only have one bullet and you cannot hit straight because, okay, you cannot hit straight. And then on 3, you have to pull the trigger. The question is, where should you aim to win the battle? So this is the steel cage, and this is elliptical steel cage. So for example, we can take this tangential line, and then we can treat this as a mirror. This is one path, right? But, so this is one path. But where should you aim if you are in this competition? Life and death. Should you aim here? Should you aim here? Where should you aim? Yeah, so this one, you don't want this because you will hit yourself. So what is your answer? Alex say either top or bottom. Anyone disagree? It's good enough for students who haven't taken this class. Okay, so there is a difference between students that take my session and the other session. Where should you aim? So using this, maybe I didn't set it up clearly. Using definition of ellipse, an ellipse, it turns out that it doesn't matter where you pull it, like aim your gun, because the distance, the total distance, R1 and R2, R1 plus R2 for the whole cage is the same. So you can aim here, R1 and R2 is, R1 plus R2 is the same. Here, the simulation is broken. So that's the answer. This is my kind of, okay, so the simulation is not broken actually, I was looking for different things. So here R1 is, let's say, the left red string, and R2 is the right red string. So at any points, the sum of these two lines are the same. So you can aim at any position. Okay. So this is analogous to in a mirror. If we design mirror correctly, like this concave mirror, we don't have to aim. Let's say we want to focus light. You don't have to focus light exactly. You don't want to hit the light. You don't want to aim the light exactly at the center. You want the lens or the mirror to be able to focus light that is off center. So let's now talk about any questions. It may show up on the exam. I think it showed up on the exam last year. So you need to understand this, because Fermat's principle of least time is very, very important, as you will see. So don't you dare asking me that question, meaning like, don't you dare not knowing what is the most important concept in geometric optics. The answer should be clear. Fermat's principle of least time. Okay, so let's say this is the mirror. And right now what we are working on is a fraction of this ellipse, which is what we call concave mirror. Right now we are learning about concave mirror. Typically, how I draw this, the mirror is on the right. So let's draw it like that. Okay, so we are ahead of time. So this is concave. So this is concave mirror. Okay. There is no reflection. We will only use law of. There is no refraction. We will only use law of reflection. And one thing that maybe it's really easy, maybe concave is a daily, it's a common term, but for me, I was always confused between concave and convex. And I think perusal in your reading, they use what, mnemonic trick, which basically, if you see the word cave, that means there is a cave that you can crawl into. So this is concave mirror. The other one is convex. This is convex. All right, so concave mirror is actually more than just a what? Just a line like this. It's actually a 3D object like this. Okay. So it's a 3D object, but in our class we draw it as a 2D object. We use it to focus light. So if light comes from infinity and they are parallel, the word that we use is collimated beam. They will be focused on a focal plane, on a focal point, which is F. Okay. So, and how to decide the shape of the mirror? How can we design a mirror that can focus light? Any guess? What principle that we should use? What principle that we should use to design this? What is the most important principle in ray optics? Fermat's principle of least time. So basically what we want to use here is we want to calculate the time required for all these rays between path 1, this is path number 1, or path number 2, path number 3, and 4, and 5. They should take the same amount of time. So how to do that? So first, I say that this light is, the name is collimated beam. Basically, these lights are parallel with respect to each other and comes from infinity. How to invoke, how to calculate the time if it comes from infinity. Okay. So there is a trick. You actually can remove most of the rays. Basically, at this point, everything is parallel. And based on that, the time from infinity to this point, they're all the same for ray number 1, 2, 3, 4, 5. Actually, there are infinite number of rays. So that's one thing. And then second, you can do arithmetic. We don't have time to do that. And one of the feedback that I get from students is that I shouldn't derive. I derive too much. So basically, you can do arithmetic, and then in the end, it turns out that this surface here or this curve is a parabola. You still remember what parabola is? Yeah, it looks like this, right? So parabola looks like this. This is probably how you learn it in your high school. What is the equation of parabola? Y is equal to ax squared. Do you still remember this or no? Yeah, good. But here, I'm just trying to explain this slide here. Here, because it's flipped by 90 degrees, it turns out that after we do a little bit math, the equation here is y squared is equal to 4 fx. And f is the distance between the lens or the mirrors and the focal point. So this is not that important, but we will use this formula soon. So basically, I just spent 5 minutes explaining why we have this formula here. It turns out that parabola is amazing. If you, let's say, want to launch a telescope, you would like to have parabolic mirrors, but it's expensive to make and it's difficult to make. So what is easier to make than a parabola? What is easier to make than a parabola? A sphere. Okay. So so here is a cross section of a sphere. It's a circle, and then if you remember, the equation of circle is here, and then you can approximate parabola using a sphere. Okay. Of course, parabola and a sphere or a circle is totally different. But as long as you promise to yourself that you will be near the principal axis or the axis of the mirror, then you should be good. So this is the reason why we will focus on spherical mirror instead of parabolic mirror. And I don't think your perusal even mentioned the word parabolic mirror. Okay, but if you want to study or want to get really crisp image, you would use parabolic surface. Okay. Any question? That's the last time I derive anything this class. No, of course not. I love deriving equations. You will see that. You will see derivation again and again. Because soon you will be in a workforce, right? You will be in a room with many other people. Everybody says interesting things, and you need to come up with something clever, and you need to be able to think. So that's my goal, to prepare you for that. Yeah, Sophia. Yeah, but yeah, but as long as you promise, as long as you are, as long as the image, like the height of the image, is not too tall, then this region here, they overlap. Okay. And it turns out that this R here, if you remember the mathematics definition or equation for a circle, is equal to 2 times F, which we will use soon. So based on this exercise, R is equal to 2 times F. R is here. This is based on the definition, like mathematical definition. And from the equation of the parabola, F is this distance here. And the reason why not X squared, because the parabola is facing like horizontally instead of vertically. Good. And then we discuss about concave and convex. And what I'm showing right now is the equation of spherical mirrors and lenses. So basically in ray optics, the equation or the math is very simple. But the tricky part is the signs. And on the exam, I will provide you with a table of those signs. So let's see. Maybe I can show you. So I posted a formula sheet for exam 4 already. No, I know why you complain that I put. Sorry, the table is not there yet. I think I made a mistake in compiling my code, but it will be there before Friday. Okay, so what is the equation for ray optics? It's 1 divided by S. S is the object distance, which is the distance between an object and the mirror, plus 1 over S prime. S for a mirror is always positive. S prime can be positive or negative. Is equal to 1 over F is equal to 2 divided by R. And F is positive for concave mirror and negative for convex mirror. Let me make it more explicit. So this is how we get 2 divided by R, because from previous slide, F is R divided by 2, or R is twice of the focal length. Okay. And S prime can be positive or negative. So if S prime is negative, what does it mean? What does it mean by S prime is negative? Okay, S prime, that means the image is virtual. That's close. The image is virtual. Okay. So if this is an object, and that means the image is here, which means that you cannot capture it using your cell phone or a screen. Inverted is, let's say if the object is like this. This is inverted. In that case, Y, instead of using S, we use Y. Y is the height of the image or object. Okay, so this is the equation, really simple. So to wake you up a little bit, I'm gonna assign an iClicker question. It's really easy. A concave mirror has a radius of curvature R of 34 centimeter. And you need to use this equation. What is the focal length F? Give me a second. Right. Let's spend less than a minute. Should be really straightforward. I think basically all of you have answered. 5 more seconds. 3, 2, 1. Good. So based on this and previous slide, R is equal to 2F. and F is equal to 34 centimeter or millimeter, I don't remember. Then R is 68 centimeter, right? Wait, sorry. Oh man, lack of sleep. So wait, what is the focal length? 2 times F. Oh, sorry. R is the 34 centimeter. No wonder. Always read the question carefully. So F is equal to R divided by 2. Good. So the answer is D. Basically, all of you answered correctly. Thank you. Excellent. Any question? Next is, there is this question. Also, I'm going to send it to iClicker. If the mirror, and think about this question. It's not a trick question. So let's read the question carefully this time. A concave mirror has a radius of curvature R of 34 centimeter, identical mirror. If the mirror is immersed in water instead of in atmosphere or in air in a vacuum, what is its focal length in water? Oh, sorry. There is no choice here. So yeah, so you can type your answer. Focal length, not the radius. Okay. And the previous focal length is 17 centimeter. All right, let's spend 15 more seconds. 5 seconds. 3, 2, 1. Okay, good. So what is the answer? So the biggest answer, the most common answer is centimeter, I think. Makes sense. I think 45 of you answered 17. So as I mentioned before, when we study mirror, there is no refraction. So everything is reflection. All the action is reflection. So it's not affected by the index of refraction. So the number stays the same. So no one says same. So 17 is the right number. Good. Any question? But on the exam, I think Ross will teach you lenses. And then lenses, there is a air or light goes from, let's say, air, glass, and air, right? That means there is refraction. And because of that, when you immerse lens in, let's say, oil or water, the focal length of a lens changes, but not for mirrors. Okay. So next is we can do a little bit more math to keep the level of rigor. So basically, if image, so again, the equation is 1 over image object distance plus 1 over image distance is equal to 1 over f. So if the image is at infinity, like this one, if the object is at infinity, where is the image located? So infinity means very big, basically. So 1 over infinity is equal to 0. What is this? Sorry. This is not what I was, let's do this one. Okay, so this is where the object is at infinity. So 1 over infinity is 0. That means 1 over s prime is equal to 1 over f. So the image is at the focal plane. let's take a step back. Another thing is that mathematically, you can classify flat mirrors as a concave mirror with radius of infinity. Mathematically, I think it's a correct statement. It's just silly, okay? So using the same equation, we should be able to come up with, this is what I want. In the end, well, you see my handwriting, you see the slide, but we should get S prime is equal to minus S. Basically, the distance, the object, the image distance is equal to the image distance is equal to the object distance, but the sign, we add negative sign because the image is virtual when we form image using a flat mirror. So this is the equation, which is exactly this equation. 2 divided by infinity is 0. That means S is equal to S prime times minus 1. So this is what we learned on Friday. And this is and we have done this iClicker question. Next is the magnification. Using trigonometry, magnification is just radius of the distance. And that distance can be horizontal or vertical because light travels along a straight path. So we can just use this slide here. Basically, just to save you time, magnification here in this textbook, magnification is a small m. In other book, they can use capital M, and here is y prime divided by y. So the height of the image divided by the height of the object divided by, and then this one is proportional to minus S prime divided by S. Okay. When we use the case for flat mirror, S prime is equal to S, and then the magnification is, okay, so let me just write it. For a plane mirror or flat mirror, S prime is equal to minus S. Right? Therefore, M is equal to minus S prime divided by S. For plane mirror only, this one is the same. No, this one is equal to minus 1. So the magnification is equal to 1 for a plane mirror. Okay? And then 1 is significant. That means there is no magnification. This mirror doesn't do any magnification. Second, the sign is also important. So minus times minus is plus. Plus sign means that the object or the image is upright instead of inverted. So you don't see yourself upside down, right? But this is another equation that will be on the equation sheet for the final exam and for the exam 4. Okay. So let's do one iClicker question here. And then do. The question is, so we have point P, this is where the object is. The question is the image formed by the mirror is real or virtual? Meaning if the S prime, or mathematically, is S prime less than 0 or bigger than 0? And for concave mirror, F is positive. I see. Okay. All right, basically all of you have answered. Let's look at the answer. Okay, good. So I understand all of you are a big fan of solar eclipse, but let's do a little bit math here. And then this is the last one, okay? Just, yeah, don't worry about getting that 1 point. Let's focus on the slide, okay? So basically, the question is, what is the sign of S prime? Right? So we can rearrange the equation into this equation here. And 1 over S, this is not right here. It should be minus here, sorry. It should be minus. Okay, so there is minus sign here. And then F is larger than S. So 1 over F is smaller than 1 minus S, right? So there is a minus sign here, but this one is still correct. So if 1 over S is negative, then 1 over S prime is negative, then S prime is negative. So the answer is virtual. So there is a typo here, which I will correct before tonight. All right, so basically we learn about different applications of flat mirrors, and we start working on concave mirror, and Ross will give lecture on a principal rays. All right. Have a nice day. Thumbs up. Yeah.
Hariadi, what's a plane mirror?
Plane mirror is a flat mirror.
It's a flat.